Hi, this is Dr. Bricker here with some hints for homework number 3. And the first one I want to talk about is 4.6. And we have two forces, F1 and F2. And we want to add a third force so that the object remains at rest, so there's no net force. So this is kind of a neat one here. We can use some of our vector skills. So really I want some force going back to the right to balance out F1 and F2, which have components over here to the left, and also this one has components up, this one has components down. We want to add a third force going here. We just have to be careful about how big we make it. So let me actually take F2 and move it over here. So essentially what I'm doing vectorially or graphically is adding these things together. Tail to head, tail to head. And then I can add the resultant vector. The resultant just means what do you get when you add them together. And to do that, I can use this plus button, and here's F3, the one that I want to add to balance this thing out. So I'm going to start it here and move it over here. And I have to adjust this to 0 degrees. You've got to get the length right. And then you can see F1 plus F2, this would be the opposite of the resultant of that because it's going in the opposite direction. And then you have to pick it up and move it over here. I've got the length right, I believe. Pick it up, move it over to the dot here to balance out those other forces. Okay, so it's kind of a neat one. Just make sure you have the length correct there by doing it that way. Might take a couple of chances just to get it there. Okay, let's look at the next one. Just one other thing about this one. Before you submit it, you actually have to move F2 back to its original location. Okay, yeah, now let's look at the next one. Okay, the next one I want to talk about is this one. A skier is sliding down a 15-degree slope. Friction is not negligible. And we want to identify all the forces that are just acting on the skier. So let's sketch this out. Okay, so here's my incline, 15 degrees. Again, we're looking at things with this being the X and Y direction, just like we did in the previous chapter. So let me just represent the skier as a box here. Okay, so these are just the forces acting on the skier. So the skier's in contact with the surface, so there's got to be a normal force here. There's got to be weight acting straight down, the force of gravity. I'll put it over here. And we've got to have friction back this way. And it's kinetic friction because the skier is actually moving. And those are the only forces actually acting on the skier. This weight, if you want, you could break it into components this way, and there's theta. This one would be the weight times the sine of theta, so mg sine theta. And this one over here would be the weight times the cosine of theta, so mg cosine theta. Okay, so pick the appropriate choice based on this free body diagram. Okay, let's look at the next one. Okay, so the next one that I want to talk about is 4.14. A constant force is applied to object A, causing it to accelerate at 6 meters per second squared. The same force is applied to object B, causing its acceleration to only be 3 meters per second squared, so half as much. Applied to object C, it causes an acceleration of 9 meters per second squared. And we want to know which has the largest mass, which has the smallest mass, and then what is the ratio of mass A to mass B. Okay, let's take a look at this. Okay, so we know Newton's second law, F is equal to ma. And what they're telling us in the problem, it's the same force. So for a given force, the greater the mass, the smaller the acceleration. So you can figure out which one has the largest mass. The largest mass for a given acceleration, the largest mass would have the smallest acceleration. So you can see that here. If this one has the smallest acceleration, it must have the biggest mass. Pretend that you're pushing a box and you're giving an equal force to the box, and now you have a bigger box, same force. What's going to happen to the acceleration? So the first couple of questions you can answer with this idea. Okay, and then if you want to figure out the ratio of the masses, it's the same force, so mass A times acceleration A is equal to mass B times acceleration B, and then that's equal to mass C times acceleration c. Okay, so they're asking this ratio, mass A over mass B. They're not asking for how much is mass A, how much is mass B. We just want the ratio of that. So we can take a look at this to solve that ratio. So mass A over mass B, I'm just taking mass B and putting it to this side of the equation. That would be acceleration B over acceleration A. So again, I've just taken mass B and put it over here, taken acceleration A, put it over here, and I get this ratio. So it's just the ratio of the accelerations. Okay, let's look at the next one. Okay, so we've got a man pulling an empty wagon, causes it to accelerate at 1.4 meters per second squared. Okay, what will the acceleration be if he pulls this with the same force, but now the wagon has a child whose mass is 3 times that of the wagon? Okay, so let's draw this one out. It's a little tricky, actually. Okay, so we have this acceleration. I'm just calling it acceleration A. When we have it's 4 meters per second squared, and when it's just the cart, which is just mass m, why don't I just call it mass m? So a given force, we get this acceleration for just mass m, and that's just pulling the empty cart. Here's a cart, I guess, and it's being pulled, and its mass is just m. Okay, and now we add a child to this cart. So here's the same cart, and now we have a child in here, happy to be pulled. The mass of the cart is still m, and the child here has a mass of 3 times the cart. So same force over here. It's just now, how much mass are you actually pulling? So ask yourself that question. You might think that it's only 3 times as massive, but it's actually something else. This total mass here is m. This total mass is 4m. This is the acceleration here. How much is this acceleration going to be? So we've got 4 times as much mass. Ask yourself how much the acceleration will be. It's really similar to the 4.14 that we just did. The little trick is to know that this is actually 4 times as massive. Okay, excellent. Let's go to the next one. Okay, so this one's actually similar to what we've been working on in the last couple of problems. It's just we have a graph here, and what's being plotted is force and acceleration. And based on this graph, we want to know what the object's mass is. So you can come anywhere you want to on the graph, pick a nice convenient point where it actually crosses the axis, crosses through a nice point. So here we have 0.5 newtons, and that corresponds to an acceleration of 2 meters per second squared. So if you use F is equal to ma, the F would be 0.5, the acceleration would be 2. Or you can come up to this point if you want. If the force is 1, the acceleration is 4, and then use Newton's second law to figure out how much the mass is. Okay, going on to the next one. We have a 1,600 kilogram car traveling along a straight road at 19 meters per second squared. 2 seconds later, okay, good, so we know how much time, the speed is 24 meters per second. What is the magnitude of the net force? Okay, so based on what we did in the previous chapters, we could figure out the acceleration. We start at 19, we end up at 24 meters per second. This takes 2 seconds. We can figure out the acceleration from kinematics, right? The final velocity is equal to the initial velocity plus at. So you can get the acceleration from that. And then we want to figure out the force. So the force is ma. Here is the m. We just figured out the a. So put those together, you can get the force. That would be the net force. Okay, so it's kind of combining what we did before with kinematics with Newton's second law. Okay, so without even sketching anything out, that's the way to do it. If I were solving the problem on paper, I'd write down mass is this, initial velocity is 19, final velocity is 24, the amount of time is 2, and then, solve for the acceleration, then use Newton's second law to get the force. Okay, let's take a look at the next one. Very small forces can have tremendous effects on the motion of very small objects. So F is equal to ma. If it's a small force, but the m is really small, the acceleration is going to be really big. So that in this problem, we're given an electron. Here's the mass of the electron. Typical force given here, 1.6 to the minus 17th newtons. And okay, starting from rest, so initial velocity is 0. How much time would it take to reach a speed of 3 times 10 to the 6th meters per second? All right, let's sketch this one out. So in a sense, this is the previous problem done in reverse. The previous problem, we wanted to figure out the net force. Here we're given the net force. We want to work backwards and figure out the time. So it's really, just the opposite. So if we have the force and the mass, which we do, I've written everything down here. This is a nice way to start the problem. You can figure out the acceleration from Newton's second law. So F divided by m is equal to the acceleration. So as far as how I would do this on my calculator, let me put these numbers in. I would have 1.6 to the minus 17th newtons, which is a kilogram meter per second squared, divided by the mass, 9.1 to the minus 31st kilograms. That will give me the acceleration. So this is a kilogram meter per second squared. The kilograms cancel out. So you can do that in your calculator, get the acceleration. Here's how I actually enter it. 1.6, and then my calculator has this E button. So this is what it looks like on the calculator. 1.6 EE, this means times 10 to the. And then, let's see, it's the minus 17th power. So you don't have to type in like 1.6 and then times and then 10 raised 10 to the minus 17th power. Strange things happen sometimes. So your calculator usually has this built-in EE button, 1.6. It might just say E. Some of them just say E. Mine says EE. But that means times 10 to the. So it saves you a lot of time. So that's just the top part. And then I would do, divided by 9.1. EE button again, and then minus 31. And then enter, you get the acceleration. Okay, so that's the new stuff from this chapter. What we really want is the time. So if you know the final speed, the initial speed is 0 because it's starting from rest. How long does it take? So we can go back to kinematics again. Same equation that we had in the previous problem. And then you can figure out the time it takes. Initial velocity is 0. Take the final velocity, divide it by the acceleration you just found to figure out the time. Okay, good. Let's go on to the next one. Okay, so in 4.31, your car is accelerating to the right from a stop. And we want to put all the forces acting on the car in this problem. Identify all the forces acting on the object and draw the free body diagram. Draw the vector starting at the black dot. The location and orientation will be graded. The exact length will not be graded, but the relative length of one to the other will be graded. So to add these forces, scoot this up a little. You use the add button here. Well, there's a normal force. That's going to be pointing straight up. Weight. That's going to be pointing back down. The drag force is going to be in the opposite direction. So it's going to have to be going to the left. This is the one that might seem a little weird to you. The frictional force on the car. It's actually going to the right. I mean, the engine is turning the tires, and then the tires are touching the pavement, and it's really the friction between the floor, between the ground and the tire that propels the car forward. So review these pages. It talks a little bit about that. But just think if you're trying to walk on ice, if there's no friction, you don't go anywhere. It's really the frictional force on your foot that propels you forward. So you're going to have normal force up, weight down. Those are equal to each other. The drag force is to the left, and then the frictional force has got to be to the right, and it has to be bigger than the drag force. So when it's talking about the relative size, that's what it means. It's got to be bigger because it's accelerating. Okay, good. Well, let's take a look at the last one. That's a little tricky to understand, the frictional force idea, but think about it in terms of trying to walk across the the ground when it's icy out. Okay, so back to the next one. Whoops. In this problem we have 3 ice skaters, number 1, 2, and 3, stand in a line, each with her hands on the shoulder of the skater in front. Skater 3 is at the rear, pushes forward on skater 2. Assume that the ice is frictionless, and again, you may want to review these pages. Draw the free body diagram of skater 2, which is in the middle. Okay, same kind of thing. Here's how you add the forces. Use this button here. All right, so let's draw this out a little bit. Okay, so here's skater 3 at the rear, here's skater 2 in the middle, here's skater 1. So these are the forces only acting on skater 2. So we've got a normal force, upward, weight, equal in magnitude, down. Then we've got the force of skater 3 on skater 2. It's a contact force. Usually you call this a normal force, but in this problem they're calling it, they're labeling it with an F and just calling it a contact force. But better would be to call it a normal force. So the force of skater 3 on skater 2. So here's skater 2. Imagine you're skater 2 and skater 3 is behind you, touching you, and that's what this force is. It's a contact force. Now you're behind skater 1 and you're pushing on skater 1. In response to that, skater 1 pushes back on you. That's a third law pair. So that's back this way. Force of skater 1 on skater 2. And that has to be equal in magnitude. There's no frictional force. If they're pushing on each other, they're not actually going to be able to go anywhere. So you just have to kind of picture it. But skater 2 pushes on skater 1. In response, skater 1 pushes back on skater 2. That's a third law pair. That's where this one's coming from. And then same thing over here. This is the force of 3 actually pushing on 2. Now if you were going to do a free body diagram of skater 3, you'd have something that looked like this. So for skater 3, you'd have, I'll just do this part of it, force of skater 2 on skater 3. So I'm not going to do the complete free body diagram of skater 3, but just to show you, this and this are actually third law pairs. Okay, great. So that's all the homework. I did most of them, not all of them, but the ones I didn't do I think are similar to the other ones. If you have any questions, just email me, and I'll talk to you soon. Bye-bye.